In this video, we're going to talk about another concentration unit, and it's probably one of the most important concentration units that you're going to learn from us, whether it's in the program or whether it's in this course or how it relates directly to the workforce. And that concentration unit is called parts per million. And parts per million is abbreviated with a PPM. All right, now the reason that I say that this is the most important concentration unit is because very often in an analytical laboratory, we are looking for very small concentrations, okay? These are very, very weak concentrations of solution. It's just basically specks of product that's dissolved in a liquid for most of the time. And the reason that that's important is because our equipment can actually go that low. So very rare do we find ourselves focused on molarities of solutions. It's just not going to happen. It's a very good concentration unit to do. It's a very good concentration unit to learn, especially one of your very first ones. And if you've taken chemistry in high school, that's probably the only concentration that they focused on. But there's more to life than molarity. There's more important things than molarity, and parts per million is one of those. All right. Okay, so let's take a look at this unit a little closer. Different people have multiple ways of talking about parts per million. And I can bring in equations, and I can bring in ratios, and I can bring in all kinds of crazy crap that you probably have no interest in learning about. So I think that the best way to learn parts per million is to understand that a part per million is equal to a milligram per liter. Bottom line, that's all that it is. So if I have a 1 part per million solution, that means one little bitty milligram is dissolved in an entire liter of solution. And we have equipment that can actually go that low. A milligram typically is a speck, people. It's a speck of product that's dissolved in a half of a 2-liter bottle of Coke, and we are able to pick up that speck. And we can actually go lower than 1 part per million if we wanted to. All right? Okay, so let's say that a laboratory wanted me to prepare a 25 milliliter or 25 ppm solution of something. You know, it doesn't matter what it is. Let's just say it's some type of compound that they give me to prepare. Okay, well, I could easily take 25 milligrams and I could dissolve this in 1 liter of water. All right, and my job is done. That's all there is to it. That's all that I have to do, right? If they want me to make a 25 ppm, then that is one of the ways that I can make it. 25 milligrams in an entire liter of water. However, the issue here is that this is often waste. Right? Maybe I don't need to make an entire liter of water. Maybe I just need to scale back a little bit and not be as wasteful and only make a little bit of what I need, especially if the solvent is not water. What if the solvent's not water? Well, we can use methanol as a solvent to do this. We can use acetone as a solvent to do this. You name it, we can choose other solvents besides water. So why would you want to waste an entire liter of methanol or an entire liter of acetone just to make this sample prep? And it's not going to work, right? So we need to be a little bit better conscientious when it comes to reagents and pricing and wastefulness in the laboratory. So if I wanted to make a 25 ppm, that's the way that I would do it, 25 milligrams in a liter. But if the directions told me you want 25 ppms and you only need 100 milliliters of it, not an entire liter. All right, well, how can we go through those types of calculations? Well, I can take a ratio and proportion here. So 25 milligrams in every liter. How many milligrams would I need in 0.1 liter, right? Now, here's the catch. You have to make sure that your units are the same. So that's why we took 100 milliliters and converted it to 0.1 liter, right? So there's 1,000 milliliters in 1 liter. So dimensional analysis told me I should take 100 mils over 1, bring in my conversion factor. So 100, there's mil on top, mil on the bottom. I need to get to liter, and there's 1,000 milli for millennia, right? A millennia is 1,000 years. So 1,000 milliliters in a liter. So 100 divided by 1,000 is 0.1. So there's my setup. Now, in order to solve this, I'll bring in my calculator. And I'll take 25 times 0.1 because we're going to cross multiply here, right? So I'm going to take 25 times 0.1, and that gives me 2.5 equals 1 times x is x. So 2.5 milligrams is what I would need to use. Dissolve it into 100 mils of solvent, whatever that solvent is, and now I've made my 25 ppm solution. All right? That's all that we've got to do with it. So let's do another example. You know that these videos are all about math, all about example problems to make sure that you feel comfortable with this. So let's say that we wanted to make 175 ppm solution of something, and let's say that we only need 50 milliliters. How can we do it? Well, we do the same thing, people. 175 milligrams in 1 liter. How many milligrams would I need for 50 mils? Over here to the side, 50 mils over 1. There's 1,000 milliliters in a liter, right? Mil on top, mil on bottom. So 50 divided by 1,000 is 0.050. So you got to make sure the units are the same. And then I do it just like before. I'll cross multiply and divide, right? So I'll take 175 times 0.05. 175 times 0.05. I hit enter. That gives me 8.75. All right. So 8.75 equals 1 times x is x. So I would need to take 8.75 milligrams of that stuff, and I would need to dissolve it in 50 mils of water, and that would give me 175 part per million solution. Okay, that's all that we're doing here, and that's all that this upcoming assignment will be. It will be how would you prepare this various concentration if this is the volume that you want. And it's just a cross ratio and proportion. That's all there is to it. Now, before I end this video, I want to talk about another unit that's becoming more and more common, and that's parts per billion, all right? And that's PPB. And PPB is even smaller. Right? If parts per million was able to pick out $1 that's counterfeit out of $1 million bills, then part per billion would be able to pick out one counterfeit dollar in $1 billion bills. It's even smaller. It's 3 orders of magnitude smaller. So parts per billion works very similar to parts per million. So a part per billion, it's not milligram per liter, it's microgram per liter. Now that's supposed to be a U, right? Micro is the mu with the gram. Some people write it like that. Some people write it with a long stem that's out in front. And then other people, like nurses, will write microgram with an MC. So you'll see this a couple of different ways, but it is a microgram, not a milligram. So you would do the same thing, right? If you had to make 25 ppb solution of something, and let's say that you have to weigh that out, right? So the 25 part per billion, well, that means 25 microgram per liter of solution. So I would take 25 micrograms, I would dissolve it up into a liter of solvent, and now I've got my 25 ppb solution. But again, it's waste, right? We don't necessarily want to do waste every time. So what if I needed to make 25 ppb and I only need, let's say, 25 milliliters of it? Well, I would do the same thing as I did before. 25 microgram over 1 liter is how many micrograms over 0.025 liter, right? So 25 mils, mil on top, mil on the bottom, and there's 1,000 mils in a liter. So 25 divided by 1,000 is 0.025. So just like before with parts per million, I cross multiply and divide. So 25 times 0.025, and that equals 0.625, and then 1 times x is x. So if I cross multiply and divide, I'll get x is equal to 0.625 micrograms. So super, super tiny amount, and quite honestly, I probably wouldn't be able to weigh this stuff out with a balance. This is just theoretical. It's just how to set up a problem and how to solve the problem. But I would probably need to make a super concentrated version first, and then use dilution to dilute it down from that point, because 0.625 micrograms is super, super tiny. So good luck trying to get that onto a balance and transferred into a volumetric flask properly. I just don't think it's going to happen. But as far as the setup, you can now see it's the same exact thing. There's no difference. It's just part per billion means microgram, okay? Now, there's one other thing I want to mention just as a quick review. We've talked about gram, right? And we've talked about milligram. So 1 gram is equal to 1,000 milligrams. That's the conversion unit that we've always used in order to go from one to another, right? Millennia, 1,000 years. So 1,000 is the number associated with milligram, okay? 1 gram, though, is 1,000,000 micrograms, okay? If you're an 80s kid, you probably remember Micro Machines. Super, super tiny little cars that you could play with. I loved them. However, this is super, super, super tiny little amounts that we have to work with in a laboratory. So there's your conversion unit for that one. So don't be surprised if the problem will tell you, now that you've figured out how many milligrams that you should weigh out, how many grams would that be on an analytical balance, right? Or now that you've figured out how many micrograms you need to weigh out, how many grams would that be if you had to go on an analytical balance? Or it could also make you go microgram to milligram. If this is how many micrograms you need, how many milligrams would you actually need to weigh out? So just be comfortable going from unit to unit, and I think that you'll be okay. Just bring in those conversion factors, and you'll be able to solve these problems without an issue, okay? So in that last example, we, I think, weighed out 0.625 micrograms. Well, how many grams would that actually be if you weighed it out? All right, so 0.625 micrograms over 1. Microgram on top, microgram goes on the bottom, and we need to go to gram. So up here is the conversion factor between the two, and it looks like it takes 1,000,000 micrograms to make a gram. So let's see how super tiny this thing is. I'm going to take 0.625, and then I'm going to divide it by 1,000,000. And there's my answer. So like I said before, good luck weighing out that small, tiny of an amount. It's just not going to happen. So you're better off making a more concentrated version in real life and then weakening that down to an order of magnitude that works for you. But as far as these problems are concerned, it's just understanding what the value means. What does the unit mean, and how do you handle it? And that's really all that we're after. If I want you to bring in dilution, I'll tell you. If I want you to do other things with it, like convert these units back and forth, I'll tell you that too in the problem. But as long as you understand that parts per billion and parts per million is micrograms per liter and milligrams per liter, then you'll be okay with the assignment, and I think that you'll be able to solve these problems based on the handful of examples that we've done so far. So now that you've watched this video, go tackle the assignment on PPM and PPB, and then we'll come back and we'll follow up another concept on making these types of solutions. Good luck.